So I think last time we stopped was where we were just beginning to say to ourselves that the magneto-ionic component in entirety can be probed within our galaxy or anything in front of us, where we can imagine a background source of a polarized emission in front of which there is a Faraday rotating medium. And we have been, of course, routinely using this where there is a discrete object located at some distance from us, and it's giving out polarized emission. And then there is a medium in between the source and us, which will cause Faraday rotation depending on the strength of the magnetic field and the electron density, a combination of the electron density and the line of sight magnetic field. But we can extend this to extended non-thermal emission from the entire galaxy. And there have been many surveys which have done this, where people have looked at the polarization properties of intensity from the extended emission. So people have done this at various frequencies, using various tools, using single dish observations versus synthesis imaging and so on. And what came out as a very striking finding was this is the Stokes parameters, basically total intensity, showing the combination of both components of the dual orthogonal polarization states. And those polarization states could be defined in any manner that you might choose. The total intensity is simply sum of the intensities in the two. And that image showed not great structure, but one saw some striking structure in the images of the Stokes parameter Q and U. And you can see that here. There is some structure here. No sign of it is visible in the total intensity. That looks nice and boringly uniform, whereas there is enormous structure here. And this was a realization point where people realized that although smooth intensity variation might be available of the non-thermal emission, while there is passage through the medium, differently Faraday rotating the signal in different areas of the sky, that imprint will show up in the way the Q and U will share the linear polarization intensity. As you know, the vector is simply rotated, right? So the share between Q and U is decided by the position angle, assuming that the polarized intensity in the linear was unchanged. And so this was a fantastic demonstration of it. And so this now can be turned around, and we can ask whether this kind of a study will allow us to decipher the way the Faraday rotating material is arranged. Okay. Of course, then you can make, trivially an image using Q and U, assuming certain position angle of the original emission. You can make an image of the rotation measure. Right? This can be done even without knowing the original state of polarization, thanks to certain spectral behavior that the Faraday rotation has. And we have seen that it depends on lambda square. So by seeing a quantity of interest, which is the position angle, and seeing how it changes as a function of frequency, we can uniquely disentangle original position angle information from how much of rotation that has happened in the intermediate medium. And you will see that it has not done anything to V. That means the original, there is no change of state of polarization in terms of its ellipticity and so on and so forth. So this is just one picture of how the polarized intensity at 1.4 gigahertz in certain direction looks like. And you will see it's pretty rich structure. And you will find that the rotation measure changes are seen on various scales, various transverse length scales or angular scales. And it provides a way now of seeing the properties of the distribution of emissivity of polarized emission on the way and the distribution of the Faraday rotating material. So this is a recent example. You can see the Stokes I intensity devoid of all the structure that you see in these images shown here. And this is for the Q and U, and this is the total polarized intensity. Then one can look for even the gradients in the polarized intensity, and people have detected fine structure, filamentary structure, which can be traced to certain components of the interstellar medium. For example, one of them is has a coincident H-alpha filament. Overall, as we know, net degree of polarization is seen to be decreasing with frequency. The apparent mean rotation measures that are seen appear to be rather small in comparison with what you see at higher frequencies. So there's something going on which might be limiting our view of the reality, and that can be simply the phenomena of depolarization. Depolarization can happen if we mix different states of polarization together. And here I would like to bring in the picture that we had of the Poincare sphere, where a vector, a polarization state was shown as a radial vector, where the x and y axis within the plane of the equator indicated Stokes parameters Q and U, and whereas the z-axis pointing along the poles of the Poincare sphere indicated the amount of circular. Now you can take a state of polarization denoted by one vector, to which if you add another state which might have an arbitrarily different polarization state, you can readily see that additions of these two vectors is not going to lead to a simple scalar sum of the vector lengths. Okay, so you will find that the net will be less than the sum of the two lengths, and this is what might be leading to depolarization. One can ask how this can happen even if the same polarization state exists in certain region. There could be regions which might have some depth. So from some depth, certain emission is emitted of the same polarization state as the one in the front. But in between, there is a medium which might Faraday rotate the state of polarization from emission coming from the back other side of the source. And you will find that now you're adding a rotated state to the original version of the state. And this addition is not going to be favorably viewed. You are going to decrease the net polarization, okay, as a fraction. And so this is what can happen. This is called back to front depolarization. And of course, similar thing can happen across the face of the sky. If there is a region, for example, like the supernova remnants seen, where the polarization vectors might be having some radial directions as their position angles. If you take without having enough angular resolution, if you take the sum total of it, the net polarization will drop, net preference for the direction will reduce significantly. And so that's the angular resolution based depolarization. And so basically in the depth as well as on the face of the source, you can have depolarization. The third depolarization that can happen is if you do not have enough spectral resolution. We have seen that we rotate the position angle or the Faraday rotation causes rotation of the position angle across frequency, and it's different at different frequencies. So you will find that if you blindly average the spectral dimension where the polarization states have been different, then you will get again reduction in the net polarization. All the studies so far seek only single rotation value, rotation measure value per pixel in the images, and which will of course be closely corresponding to the rotation measure in the foreground, or the most dominant polarized emission that you might encounter along a given line of sight. But as we just now said, we expect extended polarized emission to be well spread in depth as well. And so is the Faraday rotating material. So if you look at each image pixel, you will see different regions and different slabs along the line of sight with different Faraday depth, so to say, amount of rotation are contributing. But if you ask a given slab at a given distance of polarized emission, you will find it has a unique imprint of the amount of foreground rotation measure, okay, amount of foreground Faraday rotation. And this signature, we can ask whether we can make use of. And this signature will be available in the spectral modulation of the Stokes parameters Q and U. And this is a simple example. What will happen is, if you take a single polarization, as this is an example from UT telescope context, where it has a fixed polarization. And of course, Q and U also, you can think of them as corresponding to some fixed orientation of your receiving system. Now, somebody presents you the polarized emission with a fixed position angle at the location of the source and a Faraday rotating screen in between. You will find that that position angle has been rotated systematically as a function of frequency, proportional to lambda square. Okay, and the proportionality constant is the rotation measure. So given this, as an observer, I look at it with only fixed polarization. It is like having somebody is rotating the source polarization to me, incident on my polarizer, which is a fixed orientation, and I ask how much intensity will I see. As the person rotates the polarization state of the incident radiation on my polarizer or polarization filter, I will see a sinusoidal variation. The sinusoidal variation will have excursions on either side, which will be proportional to the amount of linearly polarized component. The rest of it, the minimum intensity I will get, will be corresponding to the randomly polarized component as well as any circular polarization component that might exist. The peaks will be separated by an amount which corresponds to realigning with my filter, and that will amount to a rotation of pi in the Faraday rotation. And so, in a sense, this distance will be inversely proportional to the rotation measure. Then I can ask at a given frequency how this sinusoidal variation will appear in terms of what phase of this sinusoidal variation, whether I'll be at null or I'll be at the peak or some arbitrary point. And that will be decided by the amount of Faraday rotation that has occurred, plus the original state of polarization in terms of its position angle. That plus the Faraday rotation at that frequency will present me a situation which, when analyzed through my filter, will give me the fractional intensity that I am expected to see based on whether it matches with my filter or not. And so, taking this point, I can always work backwards to see what the original position angle is. And so all that can be done as I have described here. You can get the degree of linear polarization, you can get the rotation measure, and you can even get the intrinsic position angle after seeing what you measure and how much it has deviated due to rotation. Now, none of what I've said so far is new. This was all well appreciated by Byrne in his classic paper of 1966, which did not attract enough attention. In fact, there was a Chris Salter when we were thinking about all this, Chris Salter recalled in his student days, there was a talk given by Peter Scheuer, apparently, titled, "What is Bern Trying to Tell Us?" This was about this particular paper. And so what Bern showed was how the depolarization can take place because of successive layers of polarized emission mixed together with layers of Faraday rotating material, and how that will result in net polarization being reduced, and how to disentangle this. And he basically showed that each one of the foreground Faraday screens, the rotation measure associated with it, will be accompanied by an imprint, a sinusoidal imprint in the spectral domain, much the way I described just now. For a given rotation measure, there will be a unique sinusoidal pattern in the spectrum. Now we can imagine that each layer of emission accompanied or modulated by a sinusoid which amounts to the foreground rotation measure is going to differ for different layers. And so this will be superposition of large number of sinusoids, but each one of them uniquely tied with a non-thermal emission, polarized emission, which is behind it. And this will help you to disentangle it through a simple Fourier analysis. Okay, and this is what he did, and in fact showed in the case of Crab Nebula. Okay, he in fact drew how the emissivity of polarized emission is distributed along the depth of the Crab Nebula emission, and how the rotation measure is different at different locations. So this is same statement here. Okay, with appropriate combination of observing frequencies and bandwidths and spectral resolution, it should be possible to perform Faraday tomography by simply Fourier transforming the spectral modulation of the observed spectrum into a set of linearly polarized intensities as a function of Faraday depth. Now, the only thing you need to take care is that spectrum is available as a function of frequency, whereas this modulation is as a function of where the argument of the sinusoid is something which is proportional to wavelength square. And so you just need to resample and relabel the spectra in lambda square, and then your job is done. So what you will get is a polarized intensity data cube, where the two-dimensional sky coordinates, the right ascension declination or whatever other coordinates you might choose to describe the plane of the sky, and the depth will be the rotation measure. And this will be analogous to the spectral line data cubes, where the frequency is the axis. And you can begin to see, and of course the standard considerations hold good in terms of the resolution you can get. How much lambda square range you have will decide the fineness in the rotation measure values that you can distinguish. So that's the spectral span and the resolution width, and the spectral scan really in terms of not the hertz, but in terms of lambda squares. And so the spectral resolution width will tell you how the unambiguous rotation measure range can be mapped. And these considerations are no different from our normal considerations and the Nyquist rate, the richness of the information, and how to sample it finely enough so that you don't have any effects of aliasing, undesired aliasing. So you will find that this can now begin to be used as a very powerful tool. Now, while I was thinking about this independently, people have actually done this, and it is now known as RM synthesis. So if you come across a term RM synthesis, you can easily relate to what I've described. These are just the sample numbers. For example, if you were to use Arecibo telescope, which is unfortunately not there now, at 1 meter wavelength, you will find that you can map things over a span of 10,000 radians per square meter in the rotation measure, with a fineness in rotation measure of the order of 15 radians. You can improve that by increasing the span in lambda square, by going to a higher frequency as well, which will extend the thing to lower lambda square. And then you can improve your resolution and so on and so forth. So anyway, these are recaps of just what I've said so far. And the volume, the volume element, you will be still left to deal with in terms of amount of depolarization that can happen if things are changing within that volume, is basically the resolution in the rotation measure and the angular resolution you have on the plane of the sky. And so that you can show based on the dependencies your different quantities have. It will amount to essentially inverse of the fractional bandwidth you will have. Okay. So if you can improve on that, you can reduce the volume of the resolution element, and then finer you go, the less will be the depolarization. Okay, so I will leave it at that. And so this was, if you were to have a point source and a simple Faraday rotating screen, and if you were to do this analysis, you will find that you can, this is the axis of Faraday rotation, and this is the declination. Of course, you could have made the map in RA dec and depth, which is what is shown here in terms of a 3D picture. But this is just one cut through that. And you can see that the peak will come at the appropriate rotation measure, and of course will correspond to the declination and the right ascension of the source. You can also make a tomograph of it, okay, where you have rotation measure axis and one of the cuts through the RA dec plane, and you can see how the material, the emissivity is distributed in terms of what is the foreground rotation measure. And you can do that for all the directions, and people have been now doing that routinely. And many of you might actually spend good part of your future years doing that, because the information that it promises to bring out is immense. This will be almost unprecedented view of the galaxy, where you are actually mapping it in 3D. Of course, one has to be mindful of the fact that the magnetic field might change its direction, and because of which the net Faraday rotation might appear to go up and then come down. And you will find that there will be, at a given rotation measure, you might have combination of something near to you and something far from you. And so you have to basically decipher the Faraday depth into a tag which will have a real distance associated with it, which will of course require you to have done some calibration by using sources of known distances. And so it might require this overall calibration to see how the rotation measure changes as a function of distance in a given line of sight. If you have that, then you might be actually on a stronger footing. Fortunately, such help is available thanks to pulsars, whose distances can otherwise be guessed reasonably well using the dispersion measure. So, this is going to be a way to go. And the SKA, the square kilometer array, has the cosmic magnetism as one of the 4 prime science drivers. So I'll probably stop here and take questions.